So good morning, folks. How you doing today? Doing that good, huh?
We're doing great, Matt. How are you?
Yeah, I am doing well, thank you.
Mhm.
Let's see.
Matt, I had one question. I was wondering if you could help me on it.
Of course.
Um, I have to log into Mildwood Math real quick and find it. It'll be a few minutes.
Okay. How's everybody else doing today? So this problem came up on the solving, came up on the messages a couple of times. It's not a bad problem, but it does have a twist or two to it. And I wanted to kind of look over some of the basic types of questions that we want to expect from 7, 4, and 5. I'm sorry to hear you've been sick. I've been feeling really sick too, actually. I think it's just the cold weather coming in, throwing everybody off. But I hope you feel better soon. So is there anything else if there's anything else, I know, Gio, you're looking for a particular problem, but if there's anything else you want to look at today, let me know. But let's go ahead and start with this solving. I think it looks a little bit, nastier than it is, mostly because it's got like all the trig functions in it. But the big observation that makes this solving not too terrible is what happens when we multiply tangent by cosine. If we remember that tangent is sine over cosine based on the quotient identity, you've got that times 8 times the cosine of t. Then those cosines kind of naturally cancel each other out. So tangent times cosine is sine. So that right-hand side is just going to turn into 8 sine t, and then the 10 sine squared t on the other side. So as soon as that happens, the fact that the question then turns into being all about sines is nice. Certainly gives it a nicer look anyway. We do want to be a little careful here. The temptation to divide by sine t can be strong here, but of course, since sine t can be 0, we can't divide by something that can be 0. So instead, we want to handle this the same way we'd handle something like 10x squared equals 8x. And ideally, we'd solve that by setting it equal to 0 because it's a quadratic, and then factor it. You could just factor it into, what you want to do with the 8 and 10 is kind of up to you. You can pull the 2 out, I suppose. Then you'd get your two solutions at x equals 0 and x equals 4/5. So, that's how we isolate that x. So we should isolate that sine t in the same way. So we get 10 sine squared t minus 8 sine t equals 0. And then factor out, again, you can do whatever you want with that too, but I'm just going to bring it out to sine t times the 5 sine t minus 4. But then zero product principle says this equals 0 when any of the factors are equal to 0. 2 is never equal to 0, so it doesn't matter. So this is going to be true when sine t equals 0 and when 5 sine t minus 4 equals 0. And that's our two equations that we have to solve from there. So yeah, getting that tangent times cosine to really just go away, leave us alone, turn into that sine, makes this problem flow. But it can seem like, are we allowed to do that? And as we've talked about, and hopefully if you've watched that video on deriving all these formulas, the idea that these trig functions give us a lot of extra manipulation tools that allow some things to simplify really nicely is part of the point. You guys want to solve the sine t equals 0 and the sine t equals 4/5 all the way out, or are you pretty comfortable with it from there? Or do you have any other questions on that problem?
I'm good with where we're at right now. I think we don't need to go any further.
Okay. Let's go ahead and do that 4/5 real quick. Just do one of them there. We would be doing that sine inverse So we'd have t equals whatever the sine inverse of 4/5 is. 4/5 is not one of our standard angles. So we would have to figure out an approximation for that. So sine inverse of 4/5. And make sure I'm in radians. So 0.927. 0.927. And that's going to be in quadrant 1. Our other answer is going to have to be in quadrant 2. So I'm going to find the other one by taking pi minus the 0.927. So pi minus that answer, 2.214. Now, of course, for a general solution, we'd add coterminals. But because there's no phase shift or compression factor, and we're looking for an answer between 0 and 2 pi, here we're just going to get that t equals 0.927 and the 2.214. And just real quick, since we're already here, sine is equal to 0 at 0 and at pi. So we could just add 0 and pi there, and we'd have the solutions for that as well, if we wanted to have the whole thing. It's the only part I was having trouble with. Which one was that? Yeah, and these in general, the hardest solvings we generally run into, once we get this kind of pattern of the two solutions in the coterminals, usually the harder solvings are the ones like that involve these quadratics. Really, even once we start throwing in the rest of the tools from chapter 7. And one of the things we talked about that seemed to help with some of you guys last time was taking that quadratic and looking at it as if it didn't have those trig functions in it. What would we do there? Well, we'd factor it. And again, we talked about it. See, if your factoring skills are needing some strengthening, this is a good time to strengthen them. So we're going to get a u equals 1 and a u equals 1/2. Then we can put those trig functions back in. So sine omega equals 1/2 and sine omega equals 1, or sine w if you prefer. It's supposed to be the Greek. And this one's even a little bit nicer in some ways because the 1/2 is one of our standard angles, and ones are nice. Sine only turns into a 1 at pi, and anything coterminal to pi. But if we're asked for answers in that first rotation, this is number 15 that I'm looking at, by the way. And then we know sine is equal to 1/2 at pi over 6 and at 5 pi over 6 in the first rotation. So that gives us a solution set fairly quickly. But yeah, having the quadratic skills and the trig skills kind of meshed together does tend to I don't know, cause us pause until we're used to it. Gio, did you find that problem that you want to look at?
Yeah, so it's from 7.4.
Okay.
It's used sum or difference formula for tangent to find the exact value for tangent negative 165 degrees.
Cool. Okay. I'll get back to those other ones. You said tangent of 160 of negative 165.
Yeah, that's correct.
So if we want an exact value means we have to find or have to be using those standard angles. And 165, negative 165 is not one of our standard angles. Our our standard angles are things like, if we go in the negative direction, things like negative 30 degrees, negative 45 degrees, and negative 60 degrees. Those are our kind of what we think of as our standard angles. Now, of course, we can do it the other direction, but this is a negative, so we're going to head in the negative direction. So if we went further, negative 90 degrees, negative 120 degrees, negative 135 degrees. And we could do this in radians too, of course, negative 150 degrees and 180 degrees. So we know exact values for these nice kind of standard angles. The trouble is, well, what if we're not at one of those nice standard angles? Well, nowadays, we just grab the calculator and ask it. We could ask the calculator what the tangent of negative 165 is, and it would just throw a value at us. But in more, kind of old-fashioned tools, you couldn't do that. What you had to do is figure out how to combine the nice angles you have to make the not nice angles you want. And then the fun thing about that process, if you want to call it a fun thing, is once you had that, so like once we have what the tangent of 165 is exactly, you'd write it down in your, kind of log book. And anytime you needed to know what the tangent of negative 165 is, again, you'd go look it up. And you wouldn't have to recalculate it over and over again. And these kind of books of trigonometric values became kind of highly prized objects for a while, until they became more widely published. Anyway, so if we're going to do this, it would be essentially our plan would be to find some nice standard angles that we know that we could either add or subtract together to make 165. So if you look at our diagram down here of standard angles, if we take that negative 135 and subtract 30, we can put together a nice negative 165. So if we looked at this as the tangent of negative 135 degrees minus 30 degrees, that's the same thing as negative 165 degrees, but it's built out of our standard angles that we know the exact values for. So we'll be able to find an exact value for this tangent ratio. Questions about that step, that bit of logic, before we go on and use the tools?
I think when I did this one, I subtracted 165 from 360 and then did it from that.
Mhm.
Does that works well?
Absolutely. Any combination that you can come up with that makes that negative 165 is great.
Okay.
So yeah, you could have done subtract 360. So many options, fortunately. It feels a little bit different sometimes when you're working with radians. So like, say for example, we had the cosine of 5 pi over 12 that we were supposed to figure out. Well, 5 pi over 12, we don't really know twelfths, but if we could build this out of either the sum or difference of two things that add together to make twelfths. So anything we could put in those two little blue circles that would either add or subtract to a 5 is going to be something that's going to add or subtract to make the 5 pi over 12. However, we'd want those fractions to reduce. So we'd want to make choices where those things reduce. So like if we picked a 4 and a 1, that would add to 5 pi over 12. And 4 pi over 12 would turn into pi over 3, which is great. But 1 pi over 12, I still don't know twelfths, so that's not helpful. But even just a 2 and a 3, that's going to reduce to pi over 6. That's going to reduce to pi over 4. So that combination will work. Those add together to make 5 pi over 12, and there are standard angles. So that'll work. But we could do lots of different combinations. We could use, say, 8 pi over 12 and 3 pi over 12 and use the subtraction. So that would be what? Divide those by 2 or divided by 4. Divided by 4. So that would be 2 pi over 3 minus pi over 4. We could use that combination. We know about 2 pi over 3. We know about pi over 4. Great, use those. So any combination that you can come up with that is built from our standard angles and adds or subtracts to make the angle that we want, and will work. That seem reasonable? You guys are quiet today. Yeah. So if we want to continue this problem, which we do, how do we handle the tangent of a difference? Well, we grab our tangent of a difference tool, or whichever, if you did it from a sum perspective, grab that tool. We know the tangent of a minus b from the tools that we constructed in 7.4 and 7.5. The tangent of a minus b, you'll look that up. I'm not expecting you guys to have these memorized, certainly, but that is the tangent of a minus the tangent of b over 1 plus the tangent of a times the tangent of b. So that's going to be the tangent of a, so our tangent of negative 135 degrees minus the tangent of 30 degrees over 1 plus the tangent of negative 135 degrees times the tangent of 30 degrees. So then we just have to figure out what those are. The tangent of 135 degrees, 135 degrees is in quadrant 3 and has that kind of 45 degree reference angle. Tangent is positive in quadrant 3, so that's just going to turn into a nice 1. So those tangent negative 135s are just a nice 1. It's a nice thing about tangent at those 45s. Tangent at 30, we know 30 degrees, same thing as that pi over 6 radians, is at the square root of 3 over 2 1/2. If we look at our unit circle, we know the tangent is the y over the x, so it's the 1/2 over the square root of 3 over 2. I would simplify that a bit by multiplying by the square root of 2 over, well, sorry, by 2 over 2. That would give us 1 over the square root of 3. So 1 over the square root of 3. Now we have to clean that up a bit more. Tangent often involves a fair amount of cleanup. It's an unfortunate thing about tangent. So we'll clean that up a little bit more, but anybody unhappy about that step? Jenna, Brianna, or Brenna? Okay, Gio, guys all happy?
So the denominator, that's a 1 plus 1 times the square root of 1 over 3, right?
Yeah.
So why don't you combine those?
Oh, I will.
it's- Oh, okay. Okay.
Yeah, I'm going to simplify this quite a bit. I just wanted to make sure that that step, that was just doing all of the substitutions. So yeah, that product is certainly, that one isn't doing us any favors. And then having fractions, particularly irrational denominator fractions in our fractions, that should upset everybody. So I'm going to multiply that by the square root of 3, top and bottom, to get a nicer square root of 3 minus 1 over the square root of 3 plus 1. And that's kind of the nicer form of our answer. Cool. You could very feasibly rationalize that denominator. It's a fairly nice denominator to rationalize. So, and just to remind you how to do that, that denominator, to rationalize a multi-term denominator, you multiply by its conjugate. I've said before that, you know, usually for these, just go ahead and leave it alone. The fact, though, that this conjugate is the denominator, that's going to simplify fairly nicely. So I do want to, I'm going to go ahead and rationalize this. But if you guys stopped here, I'd be perfectly, I would be perfectly happy with that. So that denominator would turn into what, 3 minus 1. The numerator would turn into 3 minus 2 square root of 3 plus 1 when you multiply that out. So you'd get 4 minus the square root of 3, 2 square root of 3, sorry, over 2. So the fact that this simplifies down to a nice 2 minus the square root of 3, that's, you know, that is quite a nicer answer. But usually they don't simplify quite that nicely. It's just because this happens to have its conjugate in the numerator. So if that pink stuff is overly scary, you can kind of go, just focus on the green. And it kind of depends on how well you remember your rationalizing multi-term denominators with conjugates. It's a nice thing to remember, though. It's going to come in handy for those of you going, into calculus. Remembering all these little algebraic manipulations is really handy. So it's good to practice. But you can see why doing that every time you had to find the tangent of negative 165, that would be kind of troubling. But again, you go back to your, book or your notebook or your math book or whatever you're doing, and you write that down after, presumably after somebody checks your work, and then you never have to figure out the tangent of negative 165 again. You just have it. And after a while, you build up more and more of these, and you end up having a nice set of references. Little side anecdote, during the Napoleonic Wars, one of the things that made the English Navy so dangerous is it put most of its mathematicians on, or its, military people who were more skilled with mathematics, on ships, and they navigated using a lot of these nice trigonometric tools, and their tables of trig values for navigation became military secrets. They were very important to keep from the French and all that. Where at the same time, the French put most of their mathematically oriented officers in the infantry for cannons. And that's where a lot of our tools on quadratics and projectile motion, came out of. And it's hard to say it's a coincidence that during that time you could not beat the English on the water and you couldn't beat the French on land. Is it a coincidence that that's where the mathematicians were? That's arguable, but there's some actually interesting history about some of these tools. Now, for our purposes, frankly, if you want to know what the tangent of negative 165 degrees is, the decimal approximation is probably sufficient. You'll be doing some problems like this and like this in radians, that cosine of 5 pi over 12, mostly to practice using these tools and practice these manipulations. But it does have some interesting history behind it. Okay, let's jump back up to these. Here's another use for lots of these tools are some of these kinds of questions. So this is not an uncommon scenario where we know the behavior of one type of rotation. So this, knowing that the sine of theta is 3/5, that is information about one angle or one part of a rotation or whatever we happen to be modeling. And we know some information about another rotation or another oscillating value. And we want to figure out what's going to happen when we combine these things. So what happens when this rotates and then that rotates on top of it, or some gears meshing up, whatever happens to be happening to combine these oscillations. We're curious what's going to happen when we combine these oscillations and try to test its results. And again, the nice thing is we have tools for all of these relationships. Now, again, hopefully you've watched that video on where those tools come from, or certainly you've seen in your textbook or in your the sheet you can use on your tests, those lists of these tools, because again, no one's going to ask you to memorize them. But we know that, actually I'm going to use A and B again. We know that the sine of A plus or minus B is the sine of A times the cosine of B plus or minus the sine of B cosine of A. Sometimes those are written backwards, doesn't matter. So we have that tool in our list of tools. So we see a sine of a sum. So we go, hey, I have a tool for the sine of a sum, and you go look up your tool. That's what your tool says. So you go, okay, that means we know that the sine of theta plus phi is equal to the sine of theta times the cosine of phi plus the sine of phi times the cosine of theta. So this tool, this sum and difference tool for sine, allows us to turn that into all that stuff. Okay, great. Why is that helpful? Well, we know what the sine of theta is, so we automatically know that that sine of theta is equal to 3/5. So that's great. We also know what the cosine of phi is. We know the cosine of phi is 2/3. That's also nice. But we do have to figure out what the sine of phi and what the cosine of theta are. But luckily, you actually have a fair amount of experience doing that. And I'm going to encourage you, as I always do, to draw your diagrams. But you might remember, back in chapter 6, you are often asked, if we know the sine is equal to this, find the cosine and the tangent and the secant, find all the other values. This is essentially that same question. We only want particular values though. So if the sine is equal to 3/5 in quadrant 2, then that's a 3 and that's a 5, which a little Pythagorean theorem will tell us that other side is -4. So that means theta has those side lengths in ratio. So if we're asked what's the cosine of theta, well, the cosine of theta is going to be the -4/5. And you've been doing that in kind of an isolated context for a while. We're just now doing it in other problems. For phi, we're told phi is in quadrant 4, so we're down here in quadrant 4. We're told the ratio for phi under cosine is 2/3, so that's a 2, that's a 3. And a little Pythagorean theorem would tell us that that's the square root of 5. That has to be negative because we're down in quadrant 4. I know I'm doing that Pythagorean theorem part fast, but you guys okay with all that? I got 1 yes, 2 yeses. I'll take 2 yeses. So that means our sine of phi, our sine is supposed to be our y over our r, or our opposite over hypotenuse, if you like to think about it that way. So that's going to be negative square root of 5/3. All right, so we know all those values. We can bring them all together. 3/5 and 2/3 is going to be what, 6/15 plus 4 square root of 5 after all those negatives cancel out, 15ths. So how about just 6 plus 4 square root of 5, 15ths. For the most part, the tangent and the cosine are done in exactly the same way. We've got tangent of a double angle, so we go look down at our tools, go, hey, we have a tool for that, right? And we see that the tangent of 2 times an angle is equal to 2 times the tangent of that angle over 1 minus the tangent squared of that angle. So we go, hey, that's our way of opening up tangent of a double angle to express it in terms of the angle, the original angle. So, okay, so this means this is going to be 2 times the tangent of theta over 1 minus the tangent squared of theta. And we already know how theta behaves because we diagrammed theta. So the tangent here would be the y over x, so the opposite over adjacent if you prefer. So -3/4. So 2 times -3/4 over 1 minus -3/4 squared. And then we just have to simplify that. You guys want a minute to try to simplify that, or do you want me to just simplify that? You guys probably want me to simplify it because you're being all quiet today. minute shy. It's Monday. I get it. So that'd just be 2 times -3/4. So that'd be -3/2 over 1 minus 9/16 when you square that. So -3/2 over 16 minus 9 is 7/16. -3/2 times 16/7 and reduce to an 8. So how about -24/7? Now, I said the tangent and the cosine problems are essentially very similar. The half angle formulas do have that one kind of extra issue in them. If you go look up your half angle formula for cosine, you notice the half angle formula for cosine says plus or minus the square root of 1 plus the cosine of, in this case, phi over 2. And that plus or minus is an issue because it's not, we don't get multiple answers. This is a function. So we only get either the positive or the negative. We don't get both of them. And we have to assign whether we're going to use the positive or the negative. And we do that by knowing what quadrant we're in. But it can be a little deceiving because we know that that angle phi is supposed to be in quadrant 4. So let's remind ourselves here that phi is supposed to be between 3 pi over 2 and 2 pi. So phi is in quadrant 4, and we might be tempted to think, well, cosine in quadrant 4 is positive, so this thing's going to be positive. But we're not finding the cosine of phi, we're finding the cosine of half of phi. So if we divided all these by 2, that half of phi is between pi and 3 pi over 4. Well, that's quadrant 2. And visually, if you think of, we've got phi is down here in quadrant 4. If we go only halfway, we're in quadrant 2. So what is the cosine of something in quadrant 2? Cosine in quadrant 2 is negative. So we're going to have to use that negative square root of 1 plus the cosine of phi over 2. So that is the thing that makes the half angle formulas a little bit kind of extra fun, is we've got to figure out not the sine of the kind of main angle we're talking about. We got to find the plus or minus of that half angle that we're actually finding. So that's something to be careful of. But after that, again, we know what the cosine of phi is. Actually, we were just plain given the cosine of phi. So that would be 1 plus 2/3 over 2, which we'd want to clean up. Don't like having fractions in our fractions. So I'm going to multiply top and bottom of that by that 3. So 3 plus 2 over 6. So that's negative the square root of 5/6, which would be nice of us to rationalize. So that would be the square root of what, 30/6 when you rationalize it. So these sum and difference and half angle formula tools, they're really just, you know, hey, take these tools, throw things into them, you know, no, or just, you know, if you see a double angle, hey, I can replace it with this. Or the other way, if I see this kind of structure in a problem, know that we can tighten it together and write that instead. They give us this kind of extra manipulation power to use whichever setup is advantageous for us. It does take some practice. Hopefully you guys are practicing. I know some of you are. Gosh, you guys are being quiet today. You're making me nervous.
Could you do another factoring one?
Sure. Do you have a particular one that you want to look at?
So yeah, I have some. It was from 7.3. I don't think I have the specific problem written down.
I can just find one here.
Okay.
Well, I'm gonna grab that one. And then actually there's just another kind, I'm gonna say another kind of factoring one I want to look at too. So this kind of illustrates itself as a factoring one because again, we've got a squared function and a non-squared function. It does have the issue that they don't match that we'll have to fix. So we'll look at that real quick. And if you'll give me an extra minute or two, I'd also like to look at if we had something like, say, sine 2x minus sine x equals 0. If we had to solve something like that. But let's start with this one. So the trouble here, when we look at it, we see, hey, I've got a sine of beta, that is the Greek beta, and a cosine squared of beta. So the sine squared and cosine squared tends to mean we're going to be looking at handling it like a quadratic. But gosh, it's a lot easier to do those if they're both the same trig function. Like you look back at the one we started with, the fact that this had sine squared, tangent, and cosine was really problematic. As soon as we turned that into all sines, it tends to work much nicer. So it would be nice to do that same thing. Well, luckily we know on our list of tools that the cosine squared of anything plus the sine squared of that thing is equal to 1. So the cosine squared is equal to 1 minus sine squared. So that's our primary Pythagorean identity and gives us, again, an extra manipulation tool that we can turn this cosine squared into 1 minus sine squared. Oops, squared, sorry. And that will allow us to move forward in a nicer way. So then we've got the sine of beta plus 1 equals 2 minus 2 sine squared beta. If we're going to try to factor it or handle it like a quadratic, it's good to set equal to 0. So I'm going to move everything over to one side. So add the 2 sine squared beta to one side or to the other side. Leave the plus sine beta on that side. Subtract that 2 from both sides, means I'm going to have a -1 equals 0. Kate, do you like doing the substitution where I change this to a, use instead of the signs, or do you like to stay here?
It doesn't really matter to me.
Okay. I'm gonna go ahead and stay here just because you usually do it the other way. So nice to see all of them. So one of these is going to have a 2 on them because we're trying to, figure out what to multiply to make 2 sine squared. So one of them has to have a 2, the other one has to have a 1, and then sine beta, sine beta. These both have to be 1s to get that 1. And they have to add together to make a positive sign. So I'm going to want a +2 and a -1. That's going to get us a +2 sine beta -1 sine beta for that plus sine beta. Or whatever factoring logic you like. Equals 0. So that means that 2 sine beta -1 equals 0 is going to be a solution. So sine beta equals 1/2. And sine beta plus 1 equals 0 is going to be a solution. So sine beta equals -1. If we're asked in the first rotation, we know sine is -1 when beta is equal to 3 pi over 2. If we're asked for a general solution, plus any coterminals. Sine is equal to 1/2 at pi over 6 and 5 pi over 6. Again, plus the coterminals if we're asked for a general solution. Okay, does that help?
Yes, it does. Thank you.
Yeah. And you'll notice most of these factorings do tend to be fairly nice. A lot of them do have a lead coefficient, mostly because these need to be less than 1. Because if we're going to take a sine inverse, it's got to have, that's a little smaller values. So that lead coefficient is often fairly necessary. But those factorings don't tend to be on the nastier side just because that's not what we're studying. But it is an important set of tools to be able to use. Real quick before I let you go, another use for some of these double angle formulas and angle sum and difference formulas. If we wanted to solve this for x, that sine 2x is really kind of in our way. We could presumably set these equal and say we've got sine 2x equals sine x if we want to, but then what would we do from there? Even if we tried to take the sine inverse from there, you wouldn't have just 2x equals x. You'd have 2x equals x plus a bunch of coterminals, and it'd be ugly. But if we remember, hey, we have a manipulation tool for sine 2x. You go, hey, wait, isn't that equal to something? And you go look it up. You notice that's equal to 2 sine x times cosine x, according to our double angle formula for sine, minus sine x equals 0. Well, why is that handy? Well, now we have a factor of sine x in both of those. So if we factor that out, we're left with 2 cosine x minus 1. And since that product equals 0, we're going to get solutions when sine x is equal to 0. And when cosine x is equal to, solve that for 1/2. And then we've broken it down into another one of our kind of nice problems. It's going to be 0 and pi. Cosine equals 1/2. What's cosine equal 1/2? Pi over 3 and 5 pi over 3 in the first rotation. So those double angle formulas can be handy for some of those tools as well. All right, guys, have any other questions before I let you go? Okay. Kate, I sent you a message back from one of the messages you sent me. I sent it back this morning before class. Check that out. Let me know if you want to set something up.
Okay, thank you.
Okay. If anything comes up as you guys do your prep, let me know. But then I'll talk to you later.